Hi, we're going to solve a problem called the bridge circuit in this example. And there's a picture of this circuit shown in the figure. It has 5 resistors. It's kind of laid out in a square, and the bridge is the part that goes across the diagonal. One of the variations of this problem is to say if you have some of the resistors that are known and some of the currents that are given, then you might be asked to find the total resistance of the entire network. And so that's what we'll do today. So I'm going to go ahead and first of all make the point that when we've got junctions in this circuit, I'm going to label them. We'll call this one A, we'll call this one B. And I'd like to make the point that in a circuit like this, typically a battery is connected so that it pushes current from A to B. So think about that like current flowing kind of down through this circuit from A to B. The other junctions that I didn't label yet, we're going to make this one C, and we'll make this one D. And that's going to help us to kind of set things up. All right, so now let's put in some resistance values. I think that we're going to give this resistance as 1.9 ohms. We're going to take that middle resistor. That one's going to be 3.0 ohms. And then we're going to go for this one between B and D. And that one's going to be 1.2 ohms. So those are in red. So we don't know the others, okay? And I'm just going to call this one, we're going to call this resistor here CB, because it's in between those junction points, C and B. And this one up here, we'll call this one, of course, RAD. All right, so we've got 3 of the resistors, but we don't know 2. Now, for currents, let's put those in blue. Let's say that somebody makes a measurement and they figure out that this is 2.4 amps going in that direction. And then let's say that somebody measures this current. It's moving in that direction. That one is going to be 0.8 amps. And lastly, we're going to get this current through this resistor, and that's going to be 4.6 amps. So we know the currents that go through the 3 resistors that we know their values. Okay, so now how do we go about getting the total resistance? That is the question. So total resistance in this circuit means the resistance from A to B. So if you took this entire circuit and you kind of crushed it into a single resistor, that's what we're looking for, the resistance from the top of the circuit to the bottom. Now, of course, by Ohm's law, resistance is equal to voltage from A to B. That's the battery voltage divided by the current that flows from A to B. And so that current is important. That's the total current that flows through the circuit. So that would kind of be like this. That would be the current that comes in here. That's your IAB. And that same current flows out the bottom down here. That's also IAB. So the only thing that's really not shown in this circuit is we didn't show the voltage because we didn't show the battery, but you can assume that there's some type of a battery connected to push the current, otherwise nothing would happen, right? All right, so how do we get these things, right? How do we, if we want to solve for this resistance, we got to know these 2 things. So the easiest thing to get is the voltage from A to B. And you can get that because you can use Ohm's law for each of the 3 resistors in this path. So if I go from A to C, and C to D, and D to B, if I were to add up those 3 voltage drops, that gives me the voltage from A to B. Because voltage works that way. If you're taking steps in a circuit, as long as those points are connected, the voltage has to change by each step, according to Ohm's law. So theoretically, I guess, you could say that that voltage is the voltage from A to C, plus the voltage from, plus the voltage from C to D, plus the voltage from D to B. Okay, so we've got those three numbers. Now how do you get those three numbers? Well, you look over here and say for A to C, you've got a resistance of 1.9 ohms and a current of 2.4 amps. And so you're losing voltage here. That's a voltage drop. So that voltage drop is going to be equal to I times R. So it would be a negative 2.4 times 1.9. Same thing goes for the middle branch. You're losing voltage, right? It's a voltage drop. And I times R is 0.8 times 3.0. And the last one, again, you're losing the voltage. So it's minus, 4.6 times 1.2. You get the idea, right? Now, and if you ever had a circuit where, say, one of these currents was going the other way, like, say that the current here, this 4.6, was going up, right? It sounds crazy, but sometimes it happens. If that happens, and you're following in your path, and your path takes you from D to B, you're swimming upstream here, and that would come in as a positive number. So that this last term would be positive if that current was flipped, but in this case it's not. So you end up with, doing the math, I think you get negative 12.48 volts. And that's the voltage of the battery, right? Which is kind of neat. And the fact that it's negative actually isn't all that important here, because when I go back up to the top, I'm just going to put in a 12.48. And I'll just use the absolute magnitude, because the resistance is not going to be negative, right? So we'll go with the absolute value of that number on the top. Just another point about the voltage drops, like, it doesn't matter that you're taking this path A, C, D, B. You could also take the path A, C, B. And if you knew the voltage drop in this mystery resistor here, you should really get the same number. You'd still get the 12.48. And if you really solve this whole problem with Kirchhoff's rules, you could prove that to yourself. You know, that's if you want to do that. The same thing, if you went from A to D to B, if you took the right side of the circuit, if you knew the mystery resistor and the current, you'd find out that you'd still get 12.48 volts. So as long as you're connecting the dots with your steps, you get the same voltage no matter what. And yes, it is possible through Kirchhoff's rules to find all those things, but we don't really need to in this problem. All right, so that brings us to the last part, which is currents. We need to know the current. Remember, the current from A to B, that's the total current. And I guess here, I'm going to try to convince you that if we look at the top of the circuit, this current that comes through here, right, IAB, it's got to split into two parts. And if we know one of the currents is 2.4 amps, but we got to know what the other one is. Once you know what this mystery current is from A to D, you're done. You add those two together, you're done. So I'm going to write this out. Maybe I'll do this in blue. So current from A to B is going to be equal to the current of 2.4 amps. That's the current that goes to from A to C, plus the current from A to D, which we don't know. Okay, so this is a D here, the letter D. So are we stuck? Is that kind of it? Do we know? It's like what is this current here? I'll put a question mark in the circuit. What is that? And the answer is we're not really stuck, because we can use the junction rule for junction D. And so it might seem like this is a problem here, but it's not, because let's write the junction rule for junction D. And so at junction D, what do we have? We've got 0.8 amps is flowing into junction D, 4.6 amps is flowing out, so we can count that as a negative. And then we have this mystery current. And these things have to add up to 0. So my pen is going crazy, but that's the junction rule. The currents have to sum to 0 at any junction, and D is a junction. So if you do this, it's pretty easy to show through simple math that your current from A to D is 3.8 amps. And that's the missing piece that we need to solve this part, to get the total current. So goodbye frowny face. And now if you add these two things together, you get a total current, which is equal to 2.4 plus 3.8, which is a big number. It is 6.2. And that, of course, is the number which we come back up here to. It's in amps. And that is the number that we divide by. And you can see when you do the math on this that it's 12.4 divided by 6.2. It's really close to what, like 2.0, and those are ohms. And so that's the solution to this. Now, I'm going to come back, and you might be wondering about this. You might be wondering about, well, hey, what about the bottom part of the circuit? Does this all still work? And I'll leave it as an exercise to you. I'm going to come over and have you look at CB, right? That current is not given, right? That wasn't given in the problem. But you know what? You can figure out that current like really easily. You can figure that current out by using the junction rule at junction C. Okay. By the way, it turns out, I believe it turns out to be like 1.6 amps when you do that junction rule. And what you're going to see is that 1.6 amps coming down this way, when you add it to 4.6, that's going to give you the same thing. It's going to give you your 6.2 that we got before. So isn't that neat? It's like the bottom half of the circuit, because there are two branches that are two paths that are feeding into one junction. You add the two currents from those paths, and you'd better get the same current of 6.2 amps. So that's a good check on this problem. If you were to do that bottom half of the circuit and you didn't get 6.2 amps, that means that you made a mistake with something, right? This current in the middle doesn't really add to anything, because that current in the middle, we needed it for the junction rule. But the current in the middle is not directly connected to A or B. So it's really just these two paths that feed out of A and the two paths that feed into B. So basically that's how you solve it. If you really wanted to go crazy with this, you could go backwards and you could then figure out the missing resistors. But honestly, that wouldn't really help you to find the total resistance of the circuit, because this is a complex circuit. There's no easy way to come up with series and parallel combinations of resistors to solve this, right? In case I didn't mention that at the beginning, you can't just break the circuit down and simplify it stage by stage, right? So even if you knew all 5 resistors from the beginning, you'd still have to you'd have to know some currents and go through something like this to solve it. All right, hope that was helpful.